So, welcome to everybody and good afternoon. I'm Andrew David. I'm editor at large for Elemental, and I'm going to be your host for this webinar, where, with the help of Altecnic, we're going to be taking a deep dive into the crucial role of valve technology in water safety. To take us on our tour of crucial componentry is Altecnic's product development manager, Stephanie Allchurch, and we'll be hearing from her in a few seconds. You can see her on your screen now. Of course, we want to make the session as interactive as possible, so I ask you please to post your questions in the Q&A box. You can feel free to chat away on the chat side, but the questions, please put them in the Q&A box. And we'll pose those to Steph probably at the end of the presentation. That's always the best way to do things because it allows the rhythm to carry on. So without further ado, I'm going to hand over to Steph, and I'm going to put my camera off and listen in. So welcome, Steph, and over to you.
Good afternoon, everyone. I'll just share my screen, so just bear with me for just a second. There we go. Hopefully that should be appearing in front of you any minute now.
Yep, that's on screen, Steph, so far away.
Perfect stuff. So good afternoon, everyone. I'm Stephanie Allchurch from Altecnic. Thank you to Andrew for the kind introduction there. So just a small amount about me. I deal with product development at Altecnic, and this afternoon I'm going to be talking about why valves are vital to ensure water safety in both social housing and public buildings. So while we need to ensure the water supply which is being used in any premises is clean, hygienic, and not a breeding ground for bacteria, we also need to ensure that those treatments and precautions that we take on board do not have any unintentional consequences for the end user. When it comes to showering or bathing facilities, this is even more important. While temperature is recognised as an effective control measure for bacteria, it is clear to see that hot water runs a high risk of potential scald incidents. So if we start at the beginning and look at the water system design, well, we find water systems in all buildings each come with their own challenges to supply water that is fit for purpose. Public buildings tend to have the most complex water systems, usually due to the scale or the type of property. Along with social housing, though, those public buildings have a duty of care to ensure safe water is supplied to the end user, with even greater emphasis on buildings or facilities which could be used by vulnerable people. So in particular, referring to perhaps a hospital or a care home in those sort of areas where we would find vulnerable people. So with any water system, with any building, water plays a significant role by providing water for drinking, hot and cold water to outlets, heating and cooling systems, washing facilities, and food preparation. There is an expectation that this water supply will be capable to meet the needs of the property and be available at the right point, at the right time, and at the right temperature. However, there are many challenges which can affect this. So here on screen, you'll see 3 different scenarios which all have different effects on the building and the pipework within that building. So if we consider new buildings, these should have been designed and installed considering the pipework layout, insulation, and fabric used. Clearly, if we take, for example, a building that's south-facing, perhaps the fabric is glass, and unless there were some controls in place, it would certainly suffer from increased ambient temperatures due to a result of the sunlight coming through the property. That can have some detrimental effects, clearly, with the cold water services that are running in that building, they would not be able to remain cold, and those ambient temperatures would soon increase and cause some problems. If we then look at renovations or any remedial work or extensions to a property, what we can see is that what the existing room or facility was used for originally may be repurposed to something different. So we may find that part of the water system is capped off or no longer used, or we could find that old pipework is being reused for a different purpose, and again, perhaps not exactly fit for purpose. Then finally, if we think about old buildings or historic buildings, if we take as an example a university or a hospital again, most of these are actually been around for many years and are likely to have been designed and built prior to the current design guidance. And the property will have no doubt been refurbished in many different areas and in many different ways, meaning there could be hot and cold services running in close proximity to each other, perhaps without adequate insulation. Again, there could be dead legs and redundant outlets. All of this will bring its own challenge to that property when it comes to supplying safe water for the end user. So how do we deal with this? There are many guidance documents which relate to the design of water systems and what considerations should be made as part of the design process, along with guidance specific to the control of Legionella, hygiene, safe hot water, cold water, and drinking water systems. These documents include information on best practice and risk assessment, which should be carried out prior to the facility and the pipework being installed, so that the correct control measures are in the correct location dependent on the specific requirements of the property. What you will find within these documents, and just taking a couple of different examples like HTMO 401, or even Part G of the building regulations, is that most of these refer to some level of thermostatic control as one example, and also about risk assessments being carried out on the property, ensuring that the water supply itself is having that risk assessment to understand what is the best requirements and what is best depending on who is actually using that facility. If we move on a little bit further with guidance and that trail of thought, we look at the water supply water fittings regulations. These set out the design, maintenance, and operating standards required in plumbing systems in all types of premises. They're there to protect public health and safeguard the water supply. They're predominantly there to prevent waste, misuse, undue consumption, and contamination. Within the regulations is Regulation 4, and this details the specific requirements for the components included within the water system. So as a plumbing and heating manufacturer, it's Regulation 4 that we are most interested in. If we then look at some of the certification schemes that are relevant for the UK, I've picked here just 3 schemes, RAS, NSF, and Kiwa. These are all certification schemes which help to show compliance to Regulation 4. Most reputable manufacturers will ensure their products are tested and compliant with these and are proud to show the approvals that they have on their products. However, it is interesting to understand it is not the product manufacturer's obligation to comply with Regulation 4. In fact, it is not illegal to manufacture and sell non-compliant products. Therefore, the onus is purely on the installer to ensure compliance with the water regulations, and that's at the point of install. So next we have to consider the water quality and the water hygiene. A poor installation is a major contributing factor when it comes to bacterial growth within a water system. Consideration should always be taken when new systems or remedial work on existing systems is carried out to recognise the impact this has on the water quality. Bacteria can be found in both hot and cold water systems. For bacteria not only to survive but to multiply, it must be subjected to the right environment. And there are many factors that contribute to this, but probably the two key factors are water temperature and water movement. In the images that I show there, you can see stagnant water within a tank and biofilm lined on the inside of the water pipe. Many forms of bacteria, as an example, Legionella and Pseudomonas, can live and breed within that environment. And most importantly, the biofilm can actually be food for that bacteria. So there is a real key health risk which can be transmitted from contact with waterborne pathogens, bacteria within the water systems. The transmission of the bacteria is generally contracted through airborne particles. One of the most common sources of this is cooling towers, where not only can the bacteria grow and multiply, but an outbreak can result in a large number of people being impacted by a single case. Alternatively, transmission can come from recreational activities, for example, the use of swimming pools, and even lakes and rivers, as this is not only present in man-made water systems. Vulnerable people are most likely to be affected by bacteria. Therefore, within healthcare premises, patients in ICU or neonatal units may be the most vulnerable and require additional care and services to prevent these risks. Once contracted, the bacteria usually creates a pneumonia type of illness. It can result in pneumonia or Legionnaire's disease, but it's affecting the respiratory system. So hot water provides some real advantages to bacterial control. What we want to do is we want to store hot water at no less than 60 degrees. We want to distribute at no less than 55 degrees. And if we were looking to carry out a thermal purge, then we'd probably be looking at a temperature around 70 degrees. However, it's probably no surprise that these high temperatures come with their own risks. So just to provide you with some statistics on this, there are reported 5,000 serious injuries from scalding tap water every year. And just to highlight, these statistics that I'm showing here come from the Burns database and also the Children's Burns Trust. 1,400 of these result in an overnight stay in hospital, with an average cost to the NHS for a majority burn being just under £170,000. Scalds equate to 43% of all recorded burns injury and is the highest category. And 85% of these incidents occur with children or elderly. So controlling water temperature for the end user becomes important. We want to allow high temperature hot water to circulate around the system and kill off bacteria, while removing the risk of scalding and providing stable temperatures at the point of use. We can do this by installing a thermostatic mixing valve. So a thermostatic mixing valve takes a cold water supply, say around 10 degrees, a hot water supply, in this instance we're showing at 60 degrees, and blends them together to a safe, controlled outlet temperature. Again, in this instance, we're showing 41 degrees. There are, within healthcare premises anyway, recommended temperatures for different outlets. So just to give you some indication on that, if we're talking about a basin or a shower, it would be 41 degrees. If we're talking a bath, it's 44, and actually an assisted bath where a health worker would help the person into the bath, then it's 46 degrees. If we then look at Part G of the building regulations, that stipulates that the temperature of the bath should be no more than 48 degrees. So you can see there is some guideline around what these temperatures should be. The key features of a thermostatic mixing valve is that it can work under varying supply conditions. So high and low pressures, varying flow rates, and it also incorporates a fail-safe feature, which means in the event of a failure of the cold supply, the valve will automatically react to the temperature and isolate the water supply. So if for some reason there's a blockage downstream, somebody isolates off because they're doing some remedial work on the cold water supply, anybody that goes to use the outlet that is controlled by a thermostatic mixing valve would find that they would get no water through the valve. The valves are designed to isolate off the water supply, meaning two things. The risk of scalding is taken away, and also that it's identified that there is a problem with the water supply, and some remedial work needs to happen with that to obviously get that rectified. Alternatively, the same happens with the fail-safe function if there is a blockage or an isolation of the hot water supply. It wouldn't be nice at all if anybody was suddenly in the shower and all of a sudden got dosed with cold water. So for a slightly different reason, more to do with thermal shock than anything else, the valve will also fail safe on the if there's a problem with the hot supply. So here I'm just showing a little bit more on thermostatic mixing valves and a little bit more about some specialized thermostatic mixing valves. So within the guidance documents that I was referring to earlier, so HTMO 401 as an example, there is guidance on where the thermostatic mixing valve should be installed. So really this is applicable to healthcare premises. And within that guidance, it says that the mixing valve should be situated no less than 2 meters from the outlet of the tap, shower, bath. However, this still leaves an area where bacteria can build up. So it is possible with valves like the Mixcal CareFlow Plus that you see here on the screen to conduct a thermal purge right to the outlet. This valve has a special headwork. So remove the cap from the valve, which is just a blanking cap. And under there, on top of the headwork, you see a special tool. You can use this tool to actually lift the internal mechanism. So that will completely lift the thermostatic element that's integral to these valves. And it means that you can actually bypass the valve and allow a thermal purge of that 60-degree hot water all the way to the outlet. When we come to talk about bacterial control, this is really important to ensure that there isn't any part of the system that is left to be uncontrolled or thermally purged to ensure you don't get any buildup of bacteria within that set area. So I've just touched a little bit on that thermostatic element, but just to give a little bit more detail on that. So the element that controls these thermostatic mixing valves is made up of wax and copper filings. And those will expand and contract depending on the water that comes into contact with them. And it's that allows for these fluctuations of temperatures and things like that. So with this device, we are completely physically moving that element away, allowing that bypass to go through the mixing valve to ensure that thermal purge can be undertaken. So it's not just about controlling water temperature, but also getting consistent temperature through the building too. In some public buildings where there is a large circulation network, again, like those in hospitals or care homes, you may find problems related to thermal imbalances between various risers, meaning very little hot water in zones which are furthest from the heat source, with poor circulation or high energy consumption on the recirculation pumps. You can see in the image there, the riser that is closest to the heat source has got a consistent 50 degrees, and then as that moves further away, the temperature reduces there. So what we can do is we can use a thermostatic balancing valve. This can be installed on a single branch or riser, and this will help alleviate this and balance the system to ensure all areas have the constant supply of hot water. And how the valves do this is the thermal balancing valve will control the flow rate in accordance with the water temperature by means again of a thermostatic element. When the water temperature approaches the set point of the valve, the orifice progressively closes and reduces the flow passage, reducing the amount of water recirculating. The valve can also be equipped with a thermal disinfection function, which can be useful if you wish to thermally purge the system, as this again allows for bypass. And usually we'd be looking at temperatures again in that thermal pasteurization range of around 70 degrees. So just to elaborate a little bit more on how these work, as I said, there is a thermostatic element, or referred to as a cartridge here on the cutaway that you see. There are two integral to there. One is for the set control and the other is for the disinfection control. As water always takes the easiest path, the path of least resistance, then what will happen is when the valve gets to reach its set point, it throttles down and water would then be encouraged to move further around the system where the valves are, let's say, open because they have not reached that set point as yet. So as you can see, encouraging continuous water movement is highly important. Another place we want to ensure continuous movement is on expansion vessels. These are commonly used within water systems and play an important role within them. If water is increased from 0 up to 100 degrees, it expands by approximately 4%, and therefore this water must have somewhere to go. A vessel under normal working conditions is just an empty chamber with a predetermined pre-charge of air sitting behind it. As the system volume increases, the expansion vessel fills with the increased volume of water, and when the water volume decreases, the pre-charge of air compresses down onto the bladder inside and pushes the water out of the vessel. So it's really important when installing these that the connections on the vessel are at the bottom, so you don't have any potential where water can get trapped or restricted in the vessels. A flow-through expansion vessel is designed to keep water moving through the vessel, regardless of the temperature or expansion on the system. So if we look at that a bit more, flow-through expansion vessels have an internal component in the expansion vessel connection, which assists to disperse the water, along with a flow jet valve, which sits on a T in the pipework. So this valve includes a flow diverter, which ensures that a percentage of water always flows into the vessel, meaning any water in the vessel is continuously being replenished and circulated. It also comes with a drain cock and isolation valve should a replacement vessel or membrane be required. So fitting a flow jet valve between the cold water supply pipe and the expansion vessel encourages water flow into and out of the vessel as hot water is drawn off, and more cold water flows into the cylinder. The flow of cold mains water into the bladder lowers the temperature of the mixed water, which reduces the pressure and allows the pre-charged pressure to force a small amount of water out of the vessel, thus aiding to circulation. So when we think about public buildings, it's really a complete holistic approach, from right at the very design stages all the way through to selection of valves and selection of choice for each facility. So we have thermostatic mixing valves, which provide controlled temperature water to protect the user. We have thermal balancing valves to ensure hot water remains consistent regardless of their position on the system. And we encourage water movement with our flow-through expansion vessels. So different building design and construction really do impact on water quality. Pipework layouts and maintenance are key factors in managing the risk of bacterial growth. And when using thermal disinfection as means for bacterial control, we need to ensure that those elevated temperatures are pulled through to the outlet for a complete thermal purge of the system. So I think there are 4 basic elements which we can simplify as the best course of action for any water system to ensure safe, hygienic water. And that is to simply keep it moving, keep it clean, keep the hot hot, and keep the cold cold. And that's me finished. So thank you ever so much for listening, everyone.
I'm just clicking myself back. If you just want to put your picture back on, can we see each other? That's the question. This is as I go into the
I can stop sharing my screen if I
Yes, that's probably what it is, sharing the screen. Can the audience tell that this is my first time adminning as well as hosting? Yeah, if you stop sharing your screen and I can see you and you can see me, I think that's the way it'll work. Good. There's a couple of questions come in. And I will fire away. So let's see. Let's start with the one that I had, and then we'll move on to the audience one. So, in your experience, do you think that the customers, the end users, have a sufficient understanding of the risks around water safety? One of the things I had in mind, this came to mind a few weeks ago with all the furore around the asylum seekers' boats, which had Legionella issues. And it struck me that the government, of all people, perhaps should be more understanding, have a better understanding of what causes the risks of Legionella. I mean, what are you finding out in the field, Steph?
You did say do the end users have an understanding?
Yeah, well, I mean, you can have it's both ways, isn't it? It's installers and the people that run the buildings and the installations.
Yeah, I think probably not as good as they could, and I think I think very much the end user is probably not aware at all. You know, they've read some highlights, perhaps. This is perhaps me also being very unfair to people, but I suspect, you know, there's been highlights in newspapers and things like that, and that's possibly the level of understanding. Would that be that they could understand that could be in their own home or even the car that they drive? You know, I've read things before about Legionella when a car had been sat there for a while, somebody goes to spray the screen for the first time in ages, and it's, you know, spraying bacteria all over the car window. So I don't think people are aware of how much it could affect them day to day. I think when it comes to particularly healthcare. I think because there are so many sort of guidance documents, and that the hospital probably has or will have a water safety group. They will have people that are responsible for the water supplies. I think there is certainly a more of awareness in that. But I think that's probably very much towards the commercial side of things. Whereas I do feel that probably on the domestic side of things, because the guidance is a little bit woolly when it comes to domestic, then I think it's probably that people are not so aware of it, really.
I guess the question is, what can we do about it, Steph? What can we do about it?
I think, things like this, webinars and discussions around it.
Yeah,
It really is just getting our voice out there and making ourselves heard on not to scaremonger in any way, shape, or form, just to understand that I guess everybody has that duty of care. I briefly mentioned in the presentation that it's actually not the manufacturer that takes on the responsibility of the water regulations. And very much the same when we look at, public buildings. We are relying on the water safety group, and we're relying on a risk assessment being carried out on that water system to ensure that it actually does cover everything we need. And that will take all of this into consideration. So it is quite important that that gets carried out and reviewed, because just because a risk assessment was done on a building, 10 years ago, doesn't mean that building hasn't evolved through that time period.
excellent. Thank you. That's a very great comprehensive answer, which is what we need. Here comes another one then. So, what do you think the most common misconceptions or gaps in understanding are there around valves when we're talking about safeguarding water systems? What's the most common misconception?
Sometimes, again, only because we've been talking a little bit about public buildings like healthcare but this comes to mind in particular. I talked a little bit about a mixing valve as an example should be installed no less than 2 meters to the outlet. And if there is an outbreak of bacteria within a property, then you're probably going to track that bacteria back maybe 1-2 meters from the outlet. And what do you have there? You have a thermostatic mixing valve. That thermostatic mixing valve has nothing to do with the bacteria, no different than if you went to an outlet that didn't have any thermostatic mixing valve. You trace back the bacteria to around the same point again. And sometimes, therefore, it can be a misconception on when is the right time to install a valve and when is it not. And if there is a valid reason to use these controls or not. And I think, again, going back to that risk assessment, every property is different and the users within those properties are different. So that's where this risk assessment for each property really is important, because it identifies the risks involved and thinks about the end user. Is there more a risk of bacteria buildup because, let's say, I don't know, it's in a training facility that's maybe only used once a month or every 3 months? Or is it actually in a property where people come through every day in large numbers and therefore the water system is continuously moving and continuously being replenished? Those are the sort of questions that I would expect to be asked when it comes to that risk assessment. And I think without going through that detail, that's where those misconceptions come in. And that's where we find that people will not understand the benefit of having those valves, perhaps.
Excellent. More questions coming in. So here's an either or question. Do you think we have more issues with larger domestic systems, or do we have more issues with commercial systems?
Thanks for that, Paul.
Yeah, it's pitting one area of the industry against another, Paul, I think there.
Absolutely. Look, it's difficult because guidance on domestic properties is really going down the route of guidance that HSE put out there. Okay, and with commercial properties, I mean, most of the guidance documents that I put up on that one slide are related to commercial properties. Okay, so I think the awareness and the policing is more on commercial, and therefore we see more, if that makes sense. You go looking for it, you find it. Whereas I think definitely on the domestic side, I wouldn't say, well, we're not going to look for it because there's no requirements to actually police that. It is really just going on best practice. And that's when it becomes a little bit woolly. So I would definitely steer on the side of the commercial, but that may be just because we're not actually doing the same level of detail on domestic as we do for commercial.
Again, a very good comprehensive answer. I hope the questioner is happy with that. He was obviously very excitable because he's come up with a second question. So the valves that we've spoken about today, how often do they need to be serviced and or maintained?
So if I think about there were three that I'd kind of highlighted in my presentation. So if we take a thermostatic mixing valve, again, part of this depends on where it's being installed. So as an example, if it was in a healthcare property, if we were looking at what we would say is a TMV3 thermostatic mixing valve, then I would be referring you back to the risk assessment on that particular outlet. But initially from install, there's some set criteria on checking that it's doing its job, 6 to 8 weeks, 12 to 15 weeks. But then once it's stable, I would recommend that every 6 months that should be verified. And that verification is temperature and then a fail-safe. If, of course, you did your risk assessment and said, actually, this is being used every single day, hundreds of times a day, you know, we're quite comfortable with it, then you could reduce that if you wanted to, or increase that, should I say, if you wanted to. If we take then a domestic install, a part G, let's say, bit of the building regulations where mixing valves go onto baths, that is an annual maintenance check on that valve. However, you know, it's important again to highlight these are not fit and forget valves. And I'm not entirely sure how many homeowners are aware that that valve needs to be maintained on an annual basis. And again, that probably comes back, Andrew, to your comment about we need to educate people, we need to talk about this, and so they are aware of it.
It's education, 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 Steph.
Absolutely.
They're all in the same business. Another question. So how does the choice of valves impact the maintenance costs of a system and the overall system resilience? So it's a question of, I interpret that as, is it worth forking out the money for valves? And I think I know the answer, but it'd be good to have a justification.
Yeah, do you know what? I was at a meeting just this morning and we had a very similar question come up. And mixing valves are the easiest answer on that one. I could probably give an explanation for all, but mixing valves are really a good example because you've got different types of mixing valves. You know, a bog standard, let's say, T-pattern mixing valve is absolutely fit for purpose. But upon installation, you should be testing the water temperature. You should be isolating on the cold water supply to do a fail-safe test. If you have isolation valves either side of your mixing valve as part of the mixing valve assembly, then you can immediately isolate from that point, do your fail-safe check and record the information. If you have to isolate further along the system, perhaps in another area, it can take time to get access to those isolation points, and it can slow down the time period to carry out maintenance. The, Again, the same is answered really on the thermal purge that I spoke about. You know, if you have a valve that has the ability to do that thermal purge, not only are you ensuring that you can thermally purge right to the outlet, but you're also able to speed up your process because you're doing it all from the valve itself. You're not having to remove a valve, and you're not having to leave an area which is not purged. So, yes, slightly different onset of cost initially, but obviously to speed up those regimes. And when we talk about potentially every 6 months that you're doing that, that really does become a sort of time and resource consideration to ensure that you can do that as efficiently as possible.
I guess I was thinking back to the stat you said about the number of scalding injuries. That suggests that in our estate of buildings that we are still not using valves to the extent that we should. There's more work to be done, is what that would suggest.
Yeah,
Do you
definitely.
agree?
Yes, yeah, most definitely. I mean, actually, the TMV2 scheme was generated out of the result of the need for control of hot water within the home. It was deemed that a complete submersion in hot water is the highest risk that we want to try and obviously avoid at all counts. But that is the reason the Part G of the building regs included thermostatic control on the bath, was just because there are continuously this number of scald incidents within the home. And unfortunately, I know my statistics said about it being the elderly and children, but when it's in the home, it really tends to be young children. So that really is the risk.
Excellent. Now the number of questions has ceased, which means that I have to leave you with a special question, which I always end my webinars with, and that is, if you were to boil down to one, boil down is of course the wrong phrase when we've been talking about mixing valves. If you were to reduce down what you've said today to a couple of sentences, what's the key takeaway that you want people to be thinking about?
I do think it probably is going back to sort of my last slide there, which is, the water system is the whole holistic water system. We can't just look in isolation at one particular element or one particular part, because each of those components has a knock-on effect with the other. But when it does come to control and movement of water to ensure safe water, I really think it is that keep it moving, keep it clean, keep the hot hot, and keep the cold cold, because that is just good practice for the water system.
Brilliant. Well, that brings us to the formal end of our webinar today. So, of course, we must thank you, Steph, for an excellent presentation, keeping us all engaged there. And of course, I will be reporting that the recording will be available in due course for those of you who want to catch up on some of the slides. But also, I would urge you to send it on to people who haven't been on the webinar today. That will be available very shortly at elementaldigital.co.uk. And I must thank Altecnic for being a partner in this and for sharing their knowledge, which leads me into a very nice segue. We will all be sharing more knowledge in only, he looks at his calendar, 2 months time, 2 months and 2 weeks time at the installer show, where there'll be plenty of chance for discussion, plenty of chance to meet the exhibitors, and I hope to see you all there. But for today, that's it. I hope you all have the rest of a good day. Thanks again to Steph. Thanks to you, the audience, and we will see you soon.
Thanks ever so much, everyone. Goodbye.
Thank you and goodbye.